Before we explore the properties of waves, we first have to understand what waves are. To put it simply, waves are disturbances that can travel through a medium and can transfer energy from one point to another. Such disturbances can take on two different forms: transverse waves, where oscillations are perpendicular to the direction of wave propagation, and longitudinal waves, where oscillations are parallel to the direction of wave propagation. These can be easily visualized and further explained using a slinky spring. When the slinky is stretched from each end and is at its rest position, there are obviously no waves being produced. In order to create a wave, one end of the slinky must be moved, or using technical terms, displaced vertically or horizontally. By quickly moving the end of the slinky with an up and down motion, it is now clear to see that there are waves traveling through, much like the ripples you see when a pebble is dropped in water. These are transverse waves. Observing the wave pattern, there are both high and low points being created. The high points are called crests or peaks, and the low points are called troughs. By moving the end of the slinky in a push-pull motion, a different type of wave is traveling through. These are the longitudinal waves. Observing the wave pattern, we can see that there are areas of the slinky that are compressed together, and contrastingly, areas that are not. The compressed areas are simply called compressions, and the spread out areas are called rarefactions. In general, when a wave travels through a medium, its particles are essentially being displaced from their rest position, their equilibrium. The maximum displacement it travels from this equilibrium position is called its amplitude, denoted by a capital A. The distance between two crests or peaks of a wave is called its wavelength, denoted by the Greek letter lambda. The time it takes for one whole wave to be produced is called its time period, denoted by a capital T. And if we use the equation 1 over capital T, or 1 over the time period, we get the frequency of the wave. Frequency, denoted by a lowercase f, is the number of waves produced every second. In this topic, the most important equation or relationship that you will come across involving waves, and definitely one you should remember, is v equals lambda times f, or wave speed is equal to the wavelength times frequency. Where wave speed is measured in meters per second, wavelength is measured in meters, and frequency is measured in hertz.